Okay, let's get started. All right, forms of energy. There are two main forms of energy. Oh wait, let's define energy first. So energy is the ability to cause change. So on the very top of your sheet, you have a little fill in the blank there. It says energy is the ability to cause change or do work. You can define it in both ways. So by causing change, you are in essence doing work, because the definition of work is to move something, to move a mass. Any questions so far? Okay. How are my translations so far, Christian? Provocar cambios, cause change. Is that right?
Yes. Yes.
Yeah, provocar cambios. Cool. All right, so there are two major states of energy, just like we would say states of matter, solid, liquid, gas. The two states of energy are potential energy and kinetic energy. So up also at the top of your notes, it says kinetic energy is energy of motion. It's energy of motion. So it's energy already.
Wait, so what are we supposed to be writing?
Yes. Did you get the first one right here?
I can't find the piece of paper.
Oh. Well, I'm recording this, so when you do find it, you can follow along.
Right.
Okay, but it won't. I'll try and point out when you're supposed to write something down.
Right. Do we have to write like waves and all that kind of stuff? Like,
no. All you need right now is kinetic energy is energy of motion. And potential energy is stored. So right here in the third line down, the definition, kinetic energy is energy of motion and potential energy is stored. All right, so we'll move forward here. So this is just another way of thinking about it. It's potential energy is thought of as motion waiting to happen. Kinetic energy is already in motion, already at work. So here's another spot where you're going to want to list the different forms of energy. There are 5 different forms of kinetic energy. We have electrical, thermal, mechanical, electromagnetic. Another way of saying that is light energy. And sound is the last form of kinetic energy. And you'll want to list those right here on your sheet. And then there are 3 forms of potential energy: chemical, nuclear, and mechanical. So take a second to write those ones down.
You might have to send me another copy of that piece of paper, because I don't even have it. If from the last pickup, I only have everything from social studies and ELA. So I don't have that piece of paper.
There wasn't I remember writing an envelope for you. I wrote your name on an envelope. I specifically remember that this week.
Maybe I haven't got it yet.
What? Because when I put together your envelope, Antonio, math was the only teacher who had done it so far. So I made you an envelope and I put the science stuff in it.
Let me find it then. Wait a second.
Oh.
I remember making that envelope. It's a big yellow envelope with your name on it, right? Does everybody have these written down? If not, I can get Antonio, I can get you another copy of this, no problem. But we should move on.
Yeah,
And- oh,
yeah.
go ahead.
You can copy.
You need a new copy?
Yeah.
Okay. Can make that happen. All right. So some forms of potential energy. You'll want to go to the second page of your notes for this one. So up at the top, it says the type of energy and the definition. So the definition of chemical energy is energy that is stored in bonds. So it's either stored in the bonds between atoms or in molecules, larger compounds. But anytime you break those bonds or move them around, you can release stored energy. So some examples are batteries, food, oil, anything like that. Does everybody have this one down? Energy stored in bonds, chemical. I'm gonna go forward. That's okay. Speak now. Okay, you're ready? Whoop. So energy stored in bonds. Can I go forward? All right, you don't have to write anything for nuclear energy. On the note sheet that I included on your online, there's a link you can follow on the first page if you want to learn more about nuclear energy. But nuclear energy is energy released when atoms break or combine. So an example of this is our sun. Our sun is actually nuclear energy that is transformed into light and heat energy as it leaves the sun and bathes us with its glory. But it is actually a nuclear reaction that's occurring in the sun. So we also see this in nuclear power plants. All of the stars are actually nuclear power. So you don't have to write anything for this one down, but if you are curious, there's a really good resource I put on the first page. Any questions about nuclear energy? No? Okay, so here's a picture of a nuclear power plant. You guys might have seen one of those. That's where Homer Simpson works. And then here are some pictures of chemical energy. Just to go back to chemical energy for a second. Wow, that doesn't look like pasta at all. I was telling everybody that's pasta in the bottom right-hand corner, but it doesn't look like pasta. It looks like hot dogs. Gross. So we also have wood as chemical energy, but here it is energy stored in bonds. So here's your picture of a ball and stick diagram. So this is the chemical energy. Mechanical energy can also be potential, but mechanical energy is energy due to motion or position. So up there in green, energy due to motion or position is mechanical energy. It can be either kinetic or potential. Something that is in motion is kinetic mechanical energy, or something that is like a spring. So let's take a look at some kinetic potential energy, like this guy with a bow and arrow here, these people with bow and arrows. When they pull back the string, they give it potential mechanical energy. When they stand on the edge of the plane before they fall, they have potential mechanical energy. They're going to have a lot of energy when they step out of the plane. And these types of potential energy are due to either gravity or elasticity, like a characteristic of elasticity. So you have two types of mechanical potential energy. You have a gravitational and elastic. So what's gravity? Anybody know what gravity is? It's gravity. You can type it in the chat box or raise your hand or just share out. What is gravity? Anybody? We got to chat. We got to chat.
We got a
Angel says
chat.
it keeps us on Earth. I agree, Angel. Oh, sorry, Austin. Did you find it? Looks like this on the front. So what
Are
is
you gonna
gravity? What is
Oh.
gravity? Keeps us from floating away. That's true. It also keeps Earth where it is. Keeps the sun where it is. What is gravity? Oh man, I'm so excited to teach you about gravity. I'm going to teach you about gravity on Wednesday, okay? Hang tight on gravity. Write down your questions between now and then about gravity. And we're going to talk about gravity on Wednesday, okay? It's in my book because I see we don't know anything about gravity, which is cool. That's cool. What an opportunity we have to learn about gravity. All right, so gravity will be the topic on Wednesday, but basically what you need to know now for this energy unit is the farther away you get, and here's a hint for Wednesday, the farther away you get from the center of Earth, the more gravitational potential energy you have. So those people on the plane have more gravitational potential energy than I do here standing on the floor. My golf ball has more gravitational potential energy now than it just did because I lifted it up. Just by lifting, I gave it some energy, and that will allow it to accelerate towards the center of Earth faster, just by sheer virtue of being farther away from Earth. Oops, I didn't mean to do that. There we go. I just wanted to check the chat.
You saw what?
Space because it has gravity. So sort of. Save your, Antonio, think of some good questions you want to ask about gravity and space because there's a lot of good stuff we can talk about on Wednesday. For now, let's finish though here. So we have mechanical energy, and let's talk about mechanical kinetic energy. So we talked about stored mechanical energy. Kinetic mechanical energy would be something already in motion. So Earth right now spinning is expressing kinetic energy by spinning and orbiting the sun. So mechanical energy due to motion is kinetic mechanical energy. Here are some examples. You guys have probably all seen windmills, though you've probably never seen a cheetah in the wild. I have not either, but I would really like
Cheetah.
to.
It's like the school.
So let's skip heat thermal for right now and go to electromagnetic / light. Okay, you see that on your sheet there? Oh, my electromagnetic energy just went out in the room. Electromagnetic energy is energy that travels in waves. So some examples are X-rays, gamma rays, radio waves, sunlight, and a few other things, but we can see them on the next slide as soon as you guys are ready to go. So electromagnetic energy is energy that travels in transverse waves. Here are some pictures of electromagnetic energy. So up at the top, we have the waves, and how big the waves are determines what characteristics they have. So the bigger waves are like radio waves and microwaves. And then we have infrared waves are a little bit bigger than the visible light spectrum that we see. Okay. And then we have more ultraviolet energy not ultraviolet, electromagnetic energy that we can't see in the form of ultraviolet rays, X-rays, and gamma rays. So here they are arranged from, biggest on the left to smallest on the right. And then you can see there's additional information up here. You can see penetrates Earth atmosphere. That means, can it go through our own atmosphere? Radio waves can, microwaves can't travel through air, which is interesting. Our visible light spectrum does, but much of our ultraviolet light actually, and this is really good when our atmosphere is healthy and doesn't have giant holes in it, it blocks most of the cancer causing ultraviolet light that could hit us from the sun. X-rays cannot penetrate the atmosphere very well, and neither can gamma rays. Gamma rays are emitted from nuclear energy. Any questions about all this information? Come on, I love questions. Questions tell me you're paying attention. No one? Okay. So here we go, electromagnetic energy in space traveling from the sun. This is the source of most of the energy on Earth is from our sun, which is just a medium-sized star. And we'll go back up one spot to thermal energy, okay? So thermal energy is just another way of saying heat energy. And heat energy or thermal energy is always kinetic energy because of something that we haven't really discussed yet, which is that particles are always moving. So thermal energy.
I get a question.
Yeah.
From the sun to Earth, and let's say to the moon to Earth. I wonder how fast does it move around Earth? Like counting Earth, I mean the sun and the moon. Like how fast?
Well, the moon moves around the Earth once every month. So every 30 days, the moon goes around Earth.
And the sun?
No, the moon revolves around Earth. The Earth and the moon, both together, revolve around the sun. We'll talk more about this, promise. But it looks like the sun goes up and down every day, but that's only because the Earth is spinning. Thermal energy. I hope, Antonio, I didn't get to answer your question completely, but I'm going to send you a link with a video that will explain, okay?
Okay.
All right, so thermal energy is the movement of particles. So let's take a closer look at that. Everything is made out of particles. Atoms, which is the stuff of the periodic table, right? Atoms make up everything. The faster that they move, the more heat energy, the more thermal energy they have. So let's take a look, see if this works today. It doesn't always work. Yeah, not gonna work, but let's try this instead. And I'll link this to your Google Classroom so you can play with it as well. Here, I'll just copy it right now so you can, I'll plop it in there. All right, so if we're gonna give heat energy to this substance, what did you notice happened? All right, I'm gonna take away the heat energy now. Now I'm gonna give it some more heat energy. What are you noticing?
Like when you put like the cold, they go down. When you put the fire, it goes up.
Okay. What can you say about the movement of the particles as I add heat energy?
Some of them like they go more. Oh. So when you put the heat.
What do you guys notice about the energy as you add heat? Let me get it back up here. I just want to plop that in there so you can play with it later. So you add heat. What happens to the movement of the particles?
They combine.
Well, I don't see them combining.
Mrs. Msucaro, they might get a better visual if you hit water. They can see it.
Red.
Water behaves a bit differently than some other substances. Because water, I mean, one of the properties of water that makes it super special is that it is less dense when it is in the solid form. So when it's ice, it actually spreads, and you can watch this as I heat it up. They'll actually get a little bit closer together before they get farther apart. Right there, see? So that would be close. Let's see, is it close to liquid water? Yeah, that's liquid water. And then as we heat it up, what happens to the water molecules?
They spread apart.
I'm not looking at the distance between them. I'm more looking at one molecule. All right, so here's what we're gonna do.
They go
I'm
up.
gonna back it back down. I'm gonna back it back down to 12 degrees C, okay? Now I want you to pick one molecule. That's one red one with two little white ones next to it. So pick one and watch it as I heat it up, okay? So did everybody pick a molecule?
Yes.
Pick one, watch it. Tell me what happens when I add heat. I'm gonna add heat. What happened to your molecule?
They combined.
They got all together.
They went up.
Yours went up and out of off of the bottom, Christian?
Mhm.
Yeah. Mine went faster. Did anybody's just move faster?
I mean, we can't really notice because it's a little laggy.
Yeah, it's like
Oh, okay. So play with this on your own. I won't waste any more time with it. I dropped the link on Google Classroom. Play with it on your own. See what happens when you add heat and take heat away from that system. But hopefully what you observe is as they're heating up, they're moving faster. And that can sometimes cause the distance between them to increase. And sometimes with most substances, when they cool off, they get closer together and become less dense or become more dense, less space between them. What time is it? 36. All right. Let's do the last few then, and just finish up so we don't have to do this anymore, because I hate taking notes. Electrical energy is the movement of electrons. So there's your definition for electrical. That's the very last one in your table. Electrical energy is the movement of electrons. So the flow of electrons is electricity. So when there's a current of electrons, that is electricity. Metals can conduct electricity and heat well, but things like air do not do such a great job at conducting electricity. Everybody good on that one? So here's some pictures of electricity in action. Some we're more familiar with than others. Let's do sound energy. That's right above electric energy. Sound energy is also the movement of waves, but these are longitudinal versus vertical waves. So if you put your hand on your throat when you talk, you can feel the sound energy vibrating in your throat. It is just the movement of air, right? So we have energy through a fluid. The fluid can either be air or it can be water, but there is no sound in space because there's no air in space. So once we get out of the atmosphere of Earth, there's very little sound because there's nothing for sound to pass through. Interesting. So I think we covered them all. Did we cover them all, Miss Benson? Did we do chemical, mechanical, heat, electromagnetic, sound, and electrical?
I think we did.
I think
I'm
we
trying to
did.
look through my,
All right, I'm gonna stop recording. And maybe.